my intention is eventually to talk about new work done with Erzberg and Michael Levin. But a lot of the introduction will have to do with earlier work with my student Manuel de la Torre, Erzberg, and also with Thierry Giamarchi, who's here. And this picture is something I want to explain towards the end of my talk. So as an introduction, of course, everyone here has heard about topological insulators of fermions, and the idea is that band insulators have been known for since the beginning of quantum mechanics, and describing solids and insulators in terms of band insulators being one of the triumphs of condensed matter theory, of quantum mechanics actually. But we learned to know them as something very boring fundamentally, because it's just a filled band, inert band of fermions. The point is, it was just surprisingly noticed recently that they can come in two variants, one of them which is really boring, and the other where something does happen. They're can be classified by certain topological numbers, and that implies having edge states, protected gapless edge states. So now, can we make an analogy with bosons? And the most inert and boring insulator known of bosons is the Bose-Mott insulator, where you have one particle per site. And because of interaction, so bosons like to condense, of course, in their, if they're not interacting and you put some band structure, they like to condense in the lowest band. So already getting an insulator of bosons is not completely trivial, and you have to make a lot of efforts, and experimentally it was done recently by, the last decade by Immanuel's Bloch group, and then by many other groups. So it's enough to make the interaction sufficiently strong so that the bosons at some point want to localize. But if you look at the state itself, it's quite trivial, because it's adiabatically connected to a state where there is just exactly one boson on every site. It's site factorizable. Everything is very simple. So that would be, say, the analogy to a band insulator of fermions, which is also adiabatically connected to a state which is completely site factorizable. Can we have a less trivial variant of Bose-Mott insulator that has some non-trivial topological structure and maybe protected edge states? That's maybe a general question. And sorry, the outline of my talk is, so I'll first talk about, I'll show you that there is, and we termed it Haldane insulator because of analogies with spin 1 chains. It's also, just like the Haldane phase, it is characterized by non-decaying string correlations, and it has a symmetry protecting it. It's protected by inversion symmetry, as I'll show, this kind of insulator. Then I'll show that this insulator allows for topological quantized pumping and dissipationless current inside Bose insulators. And even if we don't pump current, just the possibility to pump will set very stringent constraints on the topological nature of phase diagrams which contain both gapped and gapless phases of bosons. And that's something I want to come to. So very stringent topological constraints on phase diagrams on models which are strongly interacting and we don't even know how to solve in one and quasi one dimension, coupled chains. If there is time, I don't think there will be time, I'll talk about another topological phase which does have actually, turns out, also gapless excitations, but in the long wavelength limit are decoupled. So let me start from the first part, probably not get to the second. So as a concrete model, I want to discuss model of bosons interacting with on-site interaction and longer range interaction. And that longer range can mean nearest neighbor or even longer range. And that can be, for example, that can be realized using bosons with long-range dipolar interactions, like polar molecules, that have recently been condensed, or not condensed, but brought to near quantum degeneracy, or with atoms with large magnetic dipole moments. So in that case, you'll have a 1 over r cubed interaction. And in addition, of course, you will have hopping and on-site interaction, and that can be, in the lowest Bloch band, that looks like an extended Hubbard model. So that's the model I'll have in mind, not necessarily with 1 over r cubed interactions. And moreover, I'll focus on the particular case of integer filling, and for concreteness, let's say 1 boson per site. So let's take this model with nearest neighbor interaction now to make it simple, and ask what kind of mean field phases that you can easily get out by mean field theory, or for example, if you just look at try to minimize the interaction part of the Hamiltonian, and then, okay, when V is not present, when there is no nearest neighbor interaction, then there is just a phase transition between a superfluid and a Mott insulator. It's the usual thing, in this case in 1 dimension. But then if I look at the case where the interactions are strong and neglect the kinetic energy, I can see that there are 2 mean field phases which compete. One of them is 1 particle per site, and the other is 2-0-2-0-2-0 state, which is a charge density wave. And when V is sufficiently strong, you basically undergo a first order transition, at least in mean field theory, between this and the other phase. And
V is positive there?
V is positive. So this is very simple. You can do a mean field analysis beyond 1 boson per site, and you get various supersolids and a whole zoo of mean field phases. But my question is whether this line that is drawn in mean field theory is actually correct. And the first thing one can do is try to solve this numerically with DMRG, because it's a 1-dimensional model. Yeah.
So the previous one, why can I have a 3, 0, 0?
Oh, you can, but if you have only nearest neighbor interactions, then so if you have longer range interactions, you can have a whole sequence of charge density wave phases like that. You can have various charge density waves. But for V, if you just look at mean field theory, that's what you get. And
in which dimensions?
That's 1 dimension. I'm focusing on 1 dimension. Later, I'll also look at quasi 1 dimension when you couple 1-dimensional chains. So this is 1 dimension.
Each blue dot represents an atom?
Yeah, it's an atom, and I try to. It's red and blue because it's a little dipole, if you want.
What is the meaning of supersolid in 1 dimension?
Well, okay, it's a good question. First of all, I'm not talking about supersolid, so you don't have to think about it. Oh yeah. Okay, people say, but in principle you can have, because solid, it means breaking of the lattice symmetry, and that's a discrete symmetry. So in principle you can break discrete symmetry exactly. It's true that in 1 dimension it's hard to.
So are you saying that the number of atoms and number of sites in 1 dimension could be different?
Well, no, I'm talking about the same.
Referring to supersolid.
No, in the supersolid, it happens not at integer filling, and I'm only talking about integer filling. So
you have
integer filling,
order and breaks the discrete lattice.
Yes. So usually, I think the supersolid in 1 dimension would be power law order, and not. But you can, in principle, in certain situations, even have true long range order because you have breaking of discrete symmetry.
Why are you
so atoms
attractive?
But let's not get into that because it's really out of what I'm. Yeah.
Yeah. Why are they attractive? Is it just
Who are attractive?
bosons?
The bosons are strongly repulsive. U is large, and
I see. So
But V is larger.
V can be larger.
Okay, I got it.
If V is larger, then they might as well, pay this energy and not pay the nearest neighbor. It's a trivial thing. Okay, so now let's ask the question whether this line really persists beyond mean field theory. And I'll show you later why there is an intuitive argument that it should not persist. Yes.
But if V is large, why do you have the parameter V over T, not V over U?
Because that's the parameter I like to It doesn't matter.
No, but that would make sense if you have V over U, right? Because you have one side repulsion.
That's how I drew it. You see that
So
it
you mean that U doesn't
later,
count
later, because here I want to show you the global phase diagram, including superfluid and everything.
But this seems to be the wrong parameter then.
What is wrong and what is right? I mean,
No, you see, you have two bosons per site, and then U dominates there, right? So it looks like U has no influence on the diagram, which is kind of strange.
U is the vertical
No,
axis.
no, but you see, if you move this way.
But U is small if you move this way.
Let's continue because this is the way I want to show the phase diagram. Okay, it's not, and it's the right mean field phase diagram. You can try it. Okay, so now let's go beyond mean field, and the first thing we did is solve it using DMRG. It's a one-dimensional model. It's not trivial to solve, but possible. And it turns out that the first thing we look at is the excitation gap. What happens to the excitation gap as, say, we fix U and go on this cut, changing V from the Mott insulator and making V larger and larger. And what you see is that the excitation gap goes to 0 at this point, then goes up again and goes down again at this point. And actually, we have longer simulations where you really see it going to 0 beyond any reasonable doubt. And then it goes to a density wave phase. And the density wave phase, you can see that it's a density wave. And the question is, what is this gapped phase in the middle? It looks like two quantum phase transitions and the gapped phase in the middle.
So your dashed lines there is just some hypothetical connection, or what would
Which dashed lines?
On the right.
Oh, yeah.
In the right, in the right curve. No.
Oh, here.
Those, yeah.
Yeah. Okay, so this is a region where DMRG did not. I think now we have we can push it slightly longer, but DMRG doesn't converge well in this region. Because unless you put on a lot of, you allow for many bosons per site, and we cut the occupation basis at around 7 bosons per site. Yeah.
So, I have a question. If U is equal to infinity, don't you have basically a spin chain, XY interactions and interactions between SZs on nearest neighbors? If U is equal to infinity, does it map onto spin?
Well, in any case, it maps into a spin chain, and that's.
But a transition. Let's say
Yes.
T equals to 0, V is fine. It's just Ising model.
Oh no, Ising. It's not an Ising model. It's a spin one, say, anisotropic Heisenberg model, actually. I'll map it into, the spin chain is because of occupations, right? 0, 1, and minus 1.
Even if U is infinity, you still have a sensible model in terms of the spin. Still you have 2 parameters left, V and T. Is there a transition as a function of V over T with the U?
Well, there is also U. Oh, with U infinite.
Yes.
With U infinite, you're always going to be in this phase. You need U and V as a parameter. I'll talk about the spin model, so wait with your question in 1 second. Actually, the mapping to a spin model is what motivated us to look here for another phase, and I'll discuss it. So the first thing you can do with DMRG is just look at the first excitation gap, and you see that you have it looks like 2 quantum critical points separated and holding another phase in between this side. And you can characterize this phase a little better by looking at correlation functions. So I'm now looking at correlation. What happens to correlations as you go through the Mott insulator? So maybe this is written maybe in an inconvenient order. The first thing to look at is maybe this correlation down here, which is just the charge density wave correlation. Just density correlation function, staggered part of the density correlation function. And you see that the density correlation function at long distances is essentially 0 until you reach the charge density wave, where the second transition occurred, and the density wave correlation goes up.
Delta n is n minus 1?
Yeah, delta n is n minus 1, right? It's n minus n bar, n average. But you see that at the other transition, there is another interesting thing that happens if you look at non-local correlation functions. So one non-local correlation function that one can look at is a string correlation function, which is just like the density correlation, but the minus sign is not deterministic, but depends on the number of particles between point I and point j. Okay, so it's -1 to the particle number between I and j. This is the string order, the so-called string order parameter squared, and this is what I call a parity order parameter. And I'll show you in a second what it measures actually. So I claim that the parity order parameter is a signature, and I'll show it rigorously in a second, well, in a few slides. But the parity order parameter is a true it's a non-local order parameter of the Mott insulating phase, of the trivial Mott insulating phase. So the Mott insulating phase is constructed schematically as follows. It's delta n equals 0, 0, 0, 0 everywhere. But there is small hybridization of order T over U, which was maybe supposed to be written here, of particle Hall fluctuations built into the ground state, right? There could be virtual particle Hall fluctuations, but these always come in pairs in the Mott insulating phase. So if they come in pairs, the fact that they come in pairs means that this parity of the particle number between point I and point J would in most sectors of the ground, most parts of the superposition will be positive, and only a minority will be negative. So this parity order parameter will be non-zero. What happens in the transition to the other phase, I claim, is that these become unpaired, but they gain an alternating order. They come with an order of plus, minus, plus, minus, plus, minus. In this case, you will have, this is what the string order measures. Okay, so now I go back to the spin chain, which motivates this search for a new ground state. So the way I wrote it is having an excitation, a virtual excitation in the ground state, a virtual particle or Hall excitation is a +1 or a -1. So let me just, of course, you can have +2 and +3 because these are bosons, but if U is large, we can project to the lowest 3 occupation states, and then we have a Hilbert space of spin 1s, and I can project the Hamiltonian into the spin 1 space. It has 3 terms which looks nice, and another term which, what it means actually is breaking the up-down symmetry of the spin, and the reason of this breaking is that if I take a particle and hop it on a Mott insulator, it has a different hopping matrix element than a hole that I try to hop through because of Bose enhancement factors. So basically the only thing it shows us is that a bosonic system, which we know, doesn't have particle-hole symmetry. It has a bottom of occupation, but doesn't have a top of occupations. So let's neglect these terms. If we neglect these terms, there have been many work on this anisotropic Heisenberg model, including also on-site anisotropy, single-ion anisotropy term. And this has the following order parameter, which is a completely disordered phase here, which is analogous to the Mott insulator. It's diabatically connected with the SZ of the spin being 0 everywhere. There is this phase here, and then there is an Ising antiferromagnet. Now this phase is nothing else but connected to the Heisenberg point, which gives you the Haldane gap, the famous Haldane gap. So in that sense, that is the sense in which I mean that this phase in between. So this spin 1 model doesn't, in this parameter regime, happens not to have a superfluid phase. So but that's not very important for us because we're interested in the insulating phases. So the claim is that this insulator of bosons is completely analogous to the Haldane phase of spin 1 chains. And it's known long ago that this has a string order parameter in terms of the spin now instead of the density. And it has a breaking of a hidden Z2 symmetry.
Excuse me. So
Yes.
if we were to start with the original bosonic model, so again, the limit of large U, wouldn't it map the problem of the spin 1/2?
Yeah, but in the limit of large U, no, because you would need, it's not going to, because it's an integer filling, right? So it's integer filling, there is no, this is a half filling, or any way away from integer filling, it would map to spin 1/2. But this can never, so it's the limit of large U, it just maps to a trivial state where everything is a singlet. because you want to minimize this term, and these are spin 1s. If I go away from integer filling, then you're right. Then I can think about it as spin half. Yeah, and then it's always superfluid. Well, okay, maybe not with this term, but let's forget about non-integer filling. Okay, in order to gain more understanding of the phase transition between the Mott insulator and Haldane insulator, and that's, I'm going to neglect, I'm not going to talk about the transition, which is also interesting, into the charge density wave, but I'm going to talk about the more interesting physics that occurs in the boundary between Mott insulator and Haldane insulator, and see what protects, and I want to ask the question in the end, eventually, what protects the distinction between the Mott and Haldane insulating phases. And to do that, we need to write down a continuum theory, or a long wavelength limit that describes the transition between the two phases. I'm not going to derive it, although we can, and we derived it in this long PRB paper, but it's actually quite clear when you think about it that this is going to be the long wavelength theory. It's just a Sine-Gordon model. So it's a Sine-Gordon model that describes, you know, that this Sine-Gordon model describes the transition between superfluid and the Mott insulator. So this, when the Latinger parameter k here in these notations is larger than 2, the cosine term is irrelevant. It has a scaling dimension of 2 minus k. Sorry, k minus 2. So, sorry, yeah, 2 minus k. So this is irrelevant, but when you take k to be smaller than 2, you undergo a transition in which the lattice becomes relevant and you get a Mott insulator. But now, in the usual case where you have only on-site interaction, this G is always positive. And the fact that it's positive means something. It means that phi will be locked to 0, and in the bosonized language, that means that the particles are locked to lattice points, which is what we expect for the Mott insulator, right? Particles locked to lattice points is just this caricature wave functions with one particle on each side. What is a bit less trivial, you can actually bosonize also the parity order parameter. It's a non-local order parameter I wrote down before, which measures the parity of particles between two sites I and j, or the parity of everywhere to the left of where you're measuring, and you find that the parity operator in the long wavelength limit, the most relevant part of it is just cosine of phi. And indeed, cosine of phi in this phase, when phi is locked to 0, is non-zero. So the Mott insulating phase is indeed described by a parity order parameter, like you saw in the DMRG calculations. But it turns out that when you crank up V, when you crank up the nearest neighbor interaction or the longer range interaction, you start to renormalize this G. And that's not easy to see from a simple bosonization picture. You have to, because actually you cannot, from trivial bosonization you'll get that this G goes like U plus V. To get the minus sign correctly is a somewhat non-trivial business, but you can see that it happens. And then when it does, and G crosses sign, so first of all you see that when G changes sign, even if this is a relevant term, it's just not there, and you get a quantum phase transition that's described by a critical theory that is a Latinger liquid. But when it changes sign to become negative, phi now wants to be locked at pi over 2 rather than 0 or pi. And that means that particles will be locked to a shifted position by half a lattice constant. This is exactly at mid-lattice points. And you can write down the caricature wave function, which is this one. It looks like a site factorizable state, but it's not if you think about it, because it's a boson resonating exactly between two sites, and it's completely analogous to the AKLT wave functions for spin. So this is a caricature wave function for the Haldane phase, and what you can also see is that now, when phi is pi over 2, the expectation value of sine phi is non-zero, and that turns out to be exactly the string order parameter, or the long wavelength limit of the string order parameter. Okay, so this is a nice way to see these two different phases, and let's continue from that and ask, okay, are these really under all conditions, two different phases. Can we make them? Can we have? Well, maybe more generally, we can have a phase that has both these order parameter non-zero. So the question is what is protecting this distinction? And first, let's ask the question: is the Haldane phase stable? And of course, thermodynamically, it's stable because it's protected by a gap. But the distinction between the phases is protected just by this quantum phase transition. It's a gapless point. And the question is, what is the most relevant operator we can put here in order to undermine this gap and gap this up? And, well, you can easily see that, of course, you can put on perturbation, which is just as relevant as the cosine, and we'll gap this out, and it's a sine 2 phi term. Okay. The problem is that this sine 2 phi term does not comply with all the symmetries of the original model that I wrote down for you, because you can see it breaks particle hole symmetry, but that actually was not present in the original model anyway, so that's not important. But it also breaks inversion symmetry, and the reason is if you take x to minus x, you also take the displacement field, which is also basically like x, phi to minus phi. And taking phi to minus phi flips this term. So this is odd under inversion. This term is odd under inversion, and therefore adding a lambda term breaks the inversion symmetry we had in the original Hamiltonian. But in any and you can see immediately that if I take g through 0, of course this remains, and this remains because you can write this term as a cosine term with an extra phase chi, and this phase chi is just the arctangents of lambda over g. And what it means is, if I now by hand break the inversion symmetry in a way that's easy to do in experiment, I can tell you how. What happens now that I tune g from being positive to being negative, I simply continuously take my particles from being centered around sites to being centered somewhere off site. And that slowly changes the displacement field of the particles. And now, in this situation, both cosine phi and sine phi, both the parity and the string order parameters gain a non-zero expectation value. Another way to think about it, in terms of what I told you before, we have paired particle hole fluctuations. That's the cosine phi not being non-zero, but these pairs are now oriented. They're like oriented dipoles. Okay, so the sharp distinction between the Mott insulator and the Haldane insulator is now eliminated once we put on inversion symmetry. That's why we say that the distinction between these two phases in a bosonic system is only protected in presence of inversion symmetry. Actually, I should say in the presence of both particle hole symmetry and inversion symmetry, you need to break both particle hole symmetry and inversion symmetry in order for it to be not protected. But particle hole symmetry is anyways broken from the outset in the outset in the bosonic system, although maybe not in a spin system. So maybe that's not so important. Let me go on. Okay, so now adiabatic pumping, I already kind of hinted towards the fact that when you change g in presence of a finite lambda, you sort of move the particles around. You can make this actually more interesting and ask the question, so now we have a two-parameter space, g and lambda. G and lambda give you a two-parameter space, and in this two-parameter space, the critical point between Haldane insulator and Mott insulator is just a single point. And you can ask what happens when I carry my system adiabatically, always in the gap phase, but around the critical point. And it's very easy to see that, well, one way to see it is just look at the strong coupling limit when this cosine is very large. And in this limit, when the cosine is very large, it's clear that I'm just taking all the particles. Well, one way to think about it, this strong coupling limit is very, very small k. I'm simply taking the particles from 0 to 2 pi, is moving the particles by 1 notch, 1 lattice constant, so that I took one particle from the left side and moved it to the right side. And there is another way another very simple limit where you can see that. The other simple limit to see that is when k equals 1, you can refermionize this model and solve it as a model of free fermions. It turns out to be exactly equivalent to the Taulis model, where Taulis for the first time showed pumping of free fermions in a dimerized chain. And that turns out to be exactly the model you get when k is equal to 1 and you refermionize the model. Now, since that was also shown by Taulis and mu, the pumping of charge, it has to be integer, usually it's 0, is related to a Chern number. It's a topological number. When I change k, I cannot change suddenly this. When I change the Luttinger parameter, I cannot suddenly change the integer that I'm pumping. So if I start from k equals 1, where I can refermionize and change k, nothing will happen to the pump charge.
Can I ask a question?
Yes.
So Haldane chain has H states, and modern Slater doesn't have H states. So what happens to H states?
Exactly. Okay. Very, very, very good question. So let me answer it in 2 stages. Actually, I'm glad you asked this question. So I'm sorry I didn't have a slide on it. But mod insulator doesn't have edge states. What you're doing is you're pumping polarization here. If I pump the whole cycle, what I'm pumping is a polarization of 1. That's right. I created a polarization of 1. If I pump half a cycle, I pump from mod insulator to the Haldane insulator, I pump only half polarization, right? So I'm going to have half a boson here and half a boson here. But I can also pump the other way. If I pump in this way, I have half a boson in the other direction and half a boson in the other direction. So I have the other opposite half polarization. So going from the mod insulator, I know your question is from the other direction. I'll also discuss the other direction in a second. But if you go from the mod insulator, this pumping in one direction and the other direction gets you into the 2 different edge states if I'm on an open boundary condition. Here, so far, I discussed really periodic boundary conditions when I say pumping. But you can think about it in open boundary conditions, and then you get the edge states by pumping this way versus pumping this way. Now you can also think about it from the other direction. You start in the Haldane insulator, then you have to decide which state I start from. If I start from say the state up-down of the bosons, then I have to pump one way. The other way would not. I will not be able to pump because I have to get some half charge from the vacuum, which I don't have. So I'll only be able to pump one way this way, and from the other state the other way. What happens to the other edge state? The other edge state simply goes to the continuum somewhere here. So if I pump, of course I'm in one of the edge states. There is another unoccupied edge state. That unoccupied edge state will go into the continuum, will go up in energy and go to the continuum, and the other edge state, which I am in, will simply flow adiabatically into the mod ground state. Okay? So basically I can draw a diagram if you want. So this is 0 to pi. I have 2 edge states, but I'm in one of them. They're equal energy, but I happen to start in one. And I pump, I go to the mod ground state after pi, but this one goes up, somewhere goes up to the,
You have
this is energy.
2 edge states on each edge?
No. 2 edge state globally. It's just, I just draw the spectrum of the system.
For the spin 1 chain, there's a 4-fold degenerate.
Oh, yeah, but these are not in the boson system. Because first of all, I'm working in, the particle number is conserved. And also there is no particle hole symmetry. And because there is no particle hole symmetry, only 2 of the edge states remain degenerate, which are up, down, and down, up. The other ones are not degenerate anymore because, you prefer, say, up, up over down, down. And so, yeah.
Yes. The atoms, the charges here are dipoles, so that there's not electric charge.
Why not? Well, you can think of why there are dipoles. No, these are the charges. If
Okay,
I
so you can actually get sort of just dissipationless charge transport.
Yes. So if I had I needed reservoirs like these, say, superfluid reservoirs, for example, from the two sides, which you would get almost automatically if you had a cold atom realization of this because of this shell structure. Your chemical potential is this is an incompressible state in the middle, and in the edges you always have compressible states, and then you would get dissipationless transport from one.
But is there a solid state realization you might be able to make?
Yeah, it's a good question. There is. I don't know. There is. Actually, let's talk about it. I had in mind a few maybe options, but I don't know of a nice solid state realization. Let me show you why. I'm just going to give you one possibility for a very simple realization in cold atoms, how to change the, how to tune this parameter lambda. Lambda, remember, was the breaking of inversion symmetry, why it's very easy to tune in cold atoms. Recently, I've learned of another very, very simple way, maybe to realize it in a different system, but I can talk about it privately and maybe even easier. Both of the Haldane phase, not with any longer range interactions, and no need for another laser. So there is actually even a simpler realization, but maybe to describe it would be more complicated. So let me. But this realization involves, say, making an optical lattice with another laser that has half the wavelength. Which means that you can, by tuning the phase between the two lasers, you can make shapes that have are not sines or cosines, but have another harmonic to them. And that's the way in NIST group and in Immanuel Bloch's group, they actually realize lattices of double wells. Actually, by tuning the phase and the intensity of the second laser, you can make this double well very asymmetric, like this. And that gives you breaking of inversion symmetry. And starting from a microscopic model like this, first of all, projecting to the lowest Bloch band, you will get terms like this that break the inversion symmetry. In order to break the inversion symmetry, you cannot do it with a usual hopping term, that's Hermitian. You need an assisted hopping term. So for example, this is hopping which will be different to the right than to the left, and will depend on having some density on site I. So these terms break the inversion symmetry, and if you go to the long wavelength limit, they will automatically generate a sine term in the Latinger liquid picture, in this long wavelength picture. And you can diagonalize these by, you can look at this by with PMRG, and you see that putting on these lambda terms in the microscopic Hamiltonian will gap out the transition. You see, this is the transition from the Mott insulator to the Haldane insulator. You see the gap is 0 when lambda is equal to 0, and then it's gapped out by lambda. Now, this pumping business becomes actually much more interesting when you consider coupled chains. So let me make a brief introduction to what happens when you have coupled chains, and I'll show you why the pumping becomes a much more interesting business. So in principle, I'm considering coupled chains that have both tunneling between them and interaction between them. And that is what you will naturally get, because the dipoles interact also between chains. And if it's dipolar gases, and you can tune this interaction to some degree by changing the direction of the magnetic field compared to the plane of these chains. And you can, of course, tune the coupling, the tunnel coupling between the chains. And before going to the pumping, let me show you how this will affect the phase diagram. Okay, this is just a simple argument to show you that the string order parameter is not protected in the presence of this coupling. It's not so important. That the idea is that if you had string order in the two chains, then by coupling it with even weak T perp, you create kinks in the two chains, because hopping of a particle, if you had pluses and minuses in an alternating order here, now will not be alternating anymore. So putting on this small t-perp immediately destroys the string order, and you get decaying string correlations with a correlation length psi that goes like, scales like t-perp squared over the gap squared. Okay. Sorry, this is the inverse correlation. It's the density of kings. So the sharp distinction between Mott insulator and Haldane insulator is eliminated. What happens to the direct transition we had between the Mott insulator and the Haldane insulator? That's the next question, which will be important for the pumping issue. So let me just go over this. So now we have a Hamiltonian for chain 1, Hamiltonian for chain 2. At 0 t-perp, you have a critical point. Now you add a small t-perp. You can ask whether this this coupling between the two chains, which is just a Josephson coupling between chains, is relevant at this critical point. You find that it is relevant, and by how relevant it is, just using RG arguments, you can trace even the phase boundaries at weak coupling, weak t-perp. All this analysis is for weak is good for weak t-perp, of course. It's a low order RG in t-perp and K and G. So this gives you the phase boundaries, and you can also consider the interchain interactions, and you see that they're marginal, they're not doing anything very important. So at weak coupling, this is what happens. You open out of this Mott insulator and the Haldane insulator, you open in between a whole superfluid phase. That's weak coupling. However, okay, so just what it means for pumping for now, it just means that you open at, if you sit at some finite t-perp, let's look at a cut, with lambda here and G here, you open up a small superfluid region, you can go around it. If you go around it, you still pump one charge, because you haven't, of course, you cannot change the integer to something else by just opening this superfluid, as long as you're always going around the superfluid and you're in the gap phase. But I claim this is not the whole story, and I want to show you now that if I make t-perp and v-perp, actually for strong coupling, v-perp also matters, so I make v-perp and t-perp together strong, this superfluid phase can close here. And it will close in most cases. So then, in principle, I will have, not only in principle, I show you on numerics, I will have a diabatic connection through here somewhere in strong coupling between the Haldane and the Mott insulator. And that will bring us to a problem with the pumping, which will be solved in an interesting way. But the problem is that if this superfluid ends somewhere, then I can take this loop which pumps one charge, and maybe I can collapse it to a single point so that it maps 0 and do that continuously, and that cannot be done. So how to resolve this question? So to show you that it's a real question, let's show you that in the larger phase diagram. So now this is a phase diagram in the parameter space of G. Remember, that was the tuning parameter of between the Mott insulator and the Haldane phase. Lambda is the symmetry breaking, inversion symmetry breaking perturbation, and t-perp is just a coupling between the chains. Okay, actually it should say here t-perp and v-perp, because v-perp will also be important for strong coupling. Let's see what happens in strong coupling. So in strong coupling, let me make the following analogy. So this is a spin 1 chain, and these are the AKLT states of a spin 1 chain. So, oops. So this is an AKLT state of a spin 1 chain. Let me now think of this spin 1 chain as really composed of 2 spin halves. Just for the demonstration that I can go diabatically between the 2 chains, each in the Haldane phase, into 2 chains which are in the trivial phase, and I can do it in some path at strong coupling adiabatically. And the idea is how to do it is to increase now t-perp and v-perp, say, and these singlets now will become singlets on the vertical bonds if you increase t-perp, v-perp enough, right? And then after that you start to decrease the internal coupling here, and increase these couplings. And then these singlets will become singlets inside the sites. So you have gone from this non-trivial phase, where there are singlets across sites, into a trivial phase where there are singlets inside. So I'll show you that this is true also for a generic model, not for this kind of toy model in a second. But if you believe in me for now there is a connection between Haldane insulator and Mott insulator at strong coupling. So now look at this pumping loop that I described before at T perp equals 0. And now I can take it out of the plane to finite T perp, and I'm asking what will happen to it if I can collapse it. So how can I settle this? Let me get rid of this somehow. But I don't see, here it is. Okay. How much time do I have?
So since we have one talk cancelled, so we can have a bit more time. So
I don't need much.
We don't have an hour.
I don't need much. I mean,
so we can have this week.
okay.
Just 5-10 minutes.
Yeah, that's enough. Okay, so sorry. Yeah. So how can this be settled with an incollapsible pumping loop? And the way to settle it, the only way we can think of settling it, is that this thing cannot, the superfluid phase cannot end just as a bubble here. It has to develop some horns here that go up and down and never end, so that the pumping loop will not be able to collapse. That's the only way to resolve this seeming paradox. And this is fine, because in this case we can, in this plane of lambda equals 0, we can still connect these two phases adiabatically at sufficiently strong coupling. This should be T perp and V perp, never mind. And have an incollapsible pumping loop together with that. So that's the only way we thought of being able to resolve this question, but it looks kind of strange. How should the system know, and why should it develop these unnatural horns just because of a silly topological constraint? And so to believe ourselves in that, we went and did a numerical simulation, again with TMRG, with 2 chains. Oh, wait, before that, I'll convince you in a second, but there is another important thing. You see that when you have 2 chains and you have these horns, if we believe in these horns for a second, we have another type of loop that we can ask what happens, what's the nature of this loop. This loop corresponds to pumping how many particles. It's still an incollapsible loop. It's different from this loop topologically, and the way you can infer this is you can draw another loop like this around the other horn, and when you draw 2 loops like that, then you can connect them, and that's a continuous process. You can connect them, and they're equivalent to 1 loop. So if 2 loops are equivalent to 1 loop, and this loop pumps 2 charges, because you have 2 chains, then this loop must pump one of them, and the other loop pump the other one, because there is a symmetry between lambda and minus lambda. And another way to say it and derive this is the pump charge by this loop can be written as a Chern number, and this Chern number looks like an integral over some flux that goes through these gapless phases. And this flux is exactly 2 here for this loop, because you can say that 2 flux quanta come in this fictitious flux quanta come into this critical point, and then they have to split evenly between this branch, and when they split, each branch carries half of the flux that came in, and if these were 2 flux quanta, each one of these is 1. So I think the upshot of this is these pumping loops allow us to assign a topological index, this fictitious flux, to gapless phases in the phase diagram. And the interesting thing is that this is a much more robust classification than the classification of the gap phases, because as I showed you, the gap phases are only distinct if we don't put on T-perp, if we don't put on a symmetry breaking perturbation, but the topological index associated with the gapless phases is much more protected, and it's protected against any symmetry as long as we conserve particle number. As long as the particle number is conserved. Yes?
So the first, the big loop near the wall, which comes with the charge too,
Yes.
can you do some Berry kind of phase argument?
Yes.
This calculation?
Yes.
So that means that you can do this for this along with one of the horns of this.
Yes.
You can calculate directly and show it's a plus
Right.
12.
Right. Yes. So that actually we didn't do. We just used these topological arguments. Basically, the fact that taking two of these loops is equivalent to one of these loops. But I suppose you can do it. Well, okay. It's an interacting model. It's very hard to compute this exactly in an interacting model. We can have some non-interacting analogs of this, which are not exactly the same. Actually, in the non-interacting analog, the two horns actually sit somewhere here. There is a non-interacting analog which I can, and then we can calculate these Berry phases exactly. The way we calculated the Berry phase in this interacting model, when we had a single chain, we could refermionize it and do this for the non-interacting refermionized excitation, fermions, in the case of k equals 1. And when you have two loops, you cannot do that. So we just use these topological arguments.
So somehow basically the argument relies on the fact that you're circling around the superfluid, so it's
Yes.
that's what allows you, because of the charge non-conservation, having instead of two, and really have
Right.
a full charge. That there is some flow somewhere in the superfluid.
Instead of two, you can have one. Right.
Yeah, but I'm asking how to arrange for it. The
Oh.
only way to see to do it is probably to do something out, pump in and out of superfluid.
Yeah. To do it is you have to pump it through, you have to put superfluids on the two edges so that you will have reservoirs and be able to pump. Yes. Right. The only way to do that's
No,
what you mean?
I thought you have, maybe I misunderstood. Suppose you don't have a superfluid reservoir,
Right.
but you have just a set of chains
Yeah.
hooked up to the insulator, but inside these chains,
Right.
they already have somewhere in this parameter space superfluid, but you're saying that physically there is no superfluid anywhere.
No,
else.
physically there is no superfluid anywhere here, and the only way to really pump is to have reservoirs, as usual, right? You cannot pump freely. If you have the single chain, you can pump if you start from the right edge state. If you start from the edge state, then pumping means just going from this edge state to the other edge state. But then if you try to pump again, you'll be stuck because you cannot get another boson from the vacuum.
What if you have three chains? And you have a third one?
Well, actually, for three chains, you can show that you cannot. Actually, you can show rigorously that you cannot connect these. Then, if you have three chains of spin ones, you cannot. Then you will have to have a horn coming in the middle at least. If you have other horns, so that you cannot connect them without breaking lambda. But for two chains, so there is an even odd effect. For every odd number of chains, you cannot connect adiabatically the Mott and the Haldane insulators to lambda equals 0.
So then for 4?
And 4, you'll have, for 4 you'll have to have, you have 4 flux quanta here, so you'll have in total 2 here and 2 here. But that doesn't mean that you have 2 horns, because each horn can have 2, or you can have 3 minus, and then 1 minus 1. So the only thing that we know is that there has to be a total of 2 flux quanta going here and 2 going here, and so on as you go to higher. And it's an open, interesting question, what happens when you go to infinite number of chains? And whether you can still have some topological, and whether this fills up with gapless states, and then again there is a distinction between Mott and Haldane. I don't know. Okay, but now as I promised you, I'm going to be done very, very quickly. And just first of all, just flash this. This is a calculation with, to make it simple, we took the Bose-Hubbard model on 2 chains and projected it to 3 states per site, removed the particle hole symmetry breaking terms, the original ones, and added this lambda term. So this is just a generic model of bosons, which turned into a model of spin ones. And we looked at this phase diagram as a function of this J-perp is something that comes in here, say, and scales. V-perp and T-perp were taken with some constant ratio, I think 2 between them, okay, here. And then we added a JPERP, which increased the nearest name interchain interaction. So this is exactly the same parameter space I showed before. And these red loops show the point where it becomes gapless, and the green area is an interpolation. So all of this region is a gapless region, as inferred from the numerical calculation. And you see that the system indeed wants to develop these horns, and in the lambda equals 0 plane, you can connect the HI and Mott insulator directly, adiabatically. So this indeed works. So the last thing I wanted to show you is actually, I gave this talk in Korea, well, not the same talk exactly, but almost the same, and Victor asked me, you talked in the introduction about topological insulators of fermions, but you didn't tell us in the end how all this is related, and the fact of the matter is I didn't really know. And now I think I do know how it is related to topological insulators of fermions, and the way to understand it is to write down the topological field theory. And you can ask yourself what electrodynamic term you can write down in when you have one dimension, and which describes somehow the polarization that we're creating. And the only action you can write down is this action. It's just E, dx dt. And now the models I showed you before were invariant under inversion. Under space inversion, so naively this action is not right, because this is odd under inversion. However, I can rewrite this using the vector potential, right? This E is dt ax minus dx a naught. Now I can think of a naught is a tau. So now I can think about this as just a two-dimensional plane, x and tau, and in this two-dimensional plane, this is nothing else but the magnetic field, and I'm computing the magnetic flux out of this plane, and the magnetic flux out of this plane has to be integer. It doesn't have to be 0, naively it's 0, but you can insert a Dirac string and then make the flux go equally out of this, and you get an integer here. So this thing has to be integer. And if this has to be integer, then this theta doesn't have to be 0, as you would naively guess, but it can be either 0 or pi, and the partition function would still be invariant under inversion. So the conjecture is that the Mott, and because the Mott and Haldane phases are actually completely insulating and gapped, you can integrate out the bosons and get an action in terms of the magnetic and electric field that act on them. In this case, just electric, because it's one dimension, there is no magnetic field. And in this case, we'd say that theta equals 0 is the trivial phase. It's what the vacuum would have. It's the Mott insulator, and the Haldane phase has pi. And that pi, if you think about it, it means that there is a polarization of half in some units, which we can see in a second why. It's half along the chain, which corresponds to the edge states that you have to create in order to create this polarization. So you can either have pi or minus pi, which correspond to the two edge states. And then, and as I said, this is completely analogous to the 3D topological insulator, which has the E dot B action. So, of course, in 3 dimensions, you can write a more elaborate term like this, a more complicated term like this. And again, naively, it breaks inversion symmetry and it breaks time reversal symmetry. But if this theta is 0 or pi, even if it's pi, it's still the partition function is still invariant under these symmetries. So, but once I break the inversion symmetry in this model, theta can take any value, and then the Mott insulator and the Haldane insulator are no longer distinct. So this is a way to understand it from the field theory. And the quantized pumping, then you have to take theta, you have to give it time dependence. So if I work in a particular gauge where dx a naught is equal to 0, then this is what it is. This is the pumping, so I'm pumping polarization. And if I take theta from 0 to 2 pi, then it's just an integer value of the polarization that I pumped in going in 2 pi. Or another way to see it is to do an integration by parts, and you see that theta dot is just the current, because it couples to the vector potential. So when I take it from 0 to 2 pi, it's just integrating the current and getting some integer number So let me summarize, and I don't have time for the second part, as I suspected. I showed you that there is a new insulating phase of lattice bosons which supports non-local string correlations. It's the Haldane insulator here. The topological order is protected by lattice inversion symmetry, and that allows for, because of this two-parameter plane, it allows for adiabatic pumping of quantized charge through the insulator. And when you couple chains, you get a much more interesting pumping structure, which shows you that you can constrain the structure of the phase diagram just by infer the topological structure just because of this, of the phase diagram just because of the pumping loops, and you can associate the topological index with the gapless phases, which is much more robust than the topological protection of distinction between the two gap phases. So this is it. Thank you.
I would have expected a perf minus T perf symmetry, or that's because you have a gauge transformation?
No, there is no, because this is just, that's why I wanted to emphasize, and I forgot to put it into the talk, that this is not just T perf. It should be T perf and V perf. Okay, and when you take both of them, it doesn't have that symmetry. And the way I think about it is, if you think about it in terms of a spin model, then T perf and V perf together make a J of the spin model. And if you have ferromagnetic versus anti-ferromagnetic along the perpendicular direction, then you either have a ferromagnetic model, which gives you a effective spin 2 model, or an anti-ferromagnetic model, and these are completely different. The ferromagnetic one would be the negative here, and actually that always wants, even at strong coupling, they want to be a superfluid even more because they're larger spins. So there is no connection like this, and that's why I drew it asymmetrically. Yes. Yes.
So one of these corner superfluids, are they breaking parity?
Oh, they're breaking. Okay, there is no order parameter first of all because it's one dimension. It's a one-dimensional superfluid which and there is no parity here because parity is broken. So from the outset, it's broken by the Hamiltonian, by this lambda. So this superfluid order parameter, how would you say it breaks? Oh, you say maybe.
This is a P component.
Oh, yeah. So you say, yeah, but you see it's bosons, so I'm trying to think, how do you define the P component, because there is no internal order parameter wave function, just single bosons. What?
Maybe through the phase.
No, but the phase is still a U1 phase, because you still have breaking of spontaneous breaking. Well, if it was not one dimension, you would have spontaneous breaking of U1 symmetry. So probably you'd be hard, it's going to be hard to see this in the superfluid order parameter directly.
So I have another one. May I say that?
Yeah.
So on the previous one, when you flip through this, so the pumping deviation, this one. So this actually now you're saying the theta is a time dependent now, or is it different?
Yeah, here when you pump theta, here it's just the action of some Hamiltonian, theta, so of a particular Hamiltonian, so theta is just a static parameter. But if I now want to pump, I need to make theta time dependent, and I have to put it into the action. Yeah, so theta should be a time dependent parameter in the Hamiltonian.
So the way to ask is how to relate it to the previous pumping where you're doing an initial quasi-nice Hamiltonian. You have G, lambda, and you have chi.
Yeah. So chi is theta essentially.
Chi is theta?
Yes.
You think, or you don't?
Chi, no, I know by making indirect, by circumstantial evidence that basically chi gives me the polarization in the bosonized, and polarization couples in a theory written in terms, because that theory is not the same as the bosonized theory.
The only sort of thing there is that you really wind up chi, because the brief is constant. So I kind of agree with you.
Right, and if I compute some correlation functions like polarization, what I get out is chi. So, and this is the polarization because it couples to E. So just through this.
Kind of makes sense, but I don't know how to prove it.
Yeah. So in principle, the way to do it again is to refermionize, and in the refermionized case, you can integrate out the fermions, and get an action like that by integrating out the fermions. In the case of bosons, we don't know how to do it because the general case, because we don't know how to solve the bosonic model exactly.
Where is this, the non-interacting model you said?
Oh, yeah, what is that's an interesting, yeah, so what is the non-interacting model?
I don't know if you have time, but I was just going to ask for a reference if you have it. But
No,
if you have time to
I don't have
describe
I don't know if I have, the non-interacting model that can be...
Yeah, that you said had the horns that went out.
Oh, yeah. So the non-interacting model is, let's think first of all of one chain. So the one chain is just the Taoist model. Why is the Taoist model? The Taoist model has exactly the same kind of phase transition if you make dimerization in one sublattice versus dimerization strong on the other sublattice. It's the same nature of phase transition. And then you put two like this, and you ask, can you go from one to the other by going through the coupling through the without making any staggered field. Staggered field would be like lambda here. So without any staggered field, could you go adiabatically? And it turns out that you cannot. And the way you cannot is that there are two gapless points you have to pass when you go through this lambda equals 0 plane. T perp versus T minus T prime. And that these are the two horns are the two gapless lines. They're just lines. And you can say that this non-interacting model, for one chain, you can actually make a connection between this non-interacting model and the Haldane phase, but this is maybe we can talk privately. Okay.
Thank you, Igor, for the invitation. It's great to be here again. So this talk is difficult for me for two reasons. So I haven't slept for 24 hours, so I will try to stay awake. And the second reason is that it's probably the most mathematical talk I have ever given. So the challenge is to keep you awake. So basically today I'll be talking about, I'll give a review of some of our recent work, which is based on basically which introduces new methods to study dynamics of closed quantum systems, and it turns out that this question is related to thermodynamics of certain lattice models. And so I want to introduce basically this new technique that we are proposing. So this is the outline of the presentation. So the new technique that I'm referring to is based on mathematically on oops, is this laser pointer? Okay. It's based on what is known as Lie algebras, and it's actually a very simple concept, although it's not very much in practical calculations. And first I will sort of introduce very briefly what they are, and then using this mathematical construction I will discuss quantum dynamics of closed systems, and sort of the punchline of the first part of the talk, this is sort of single particle dynamics, would be that unitary dynamics of quantum system is essentially decoupled from the Hilbert space in which it occurs, which means that if you have, for instance, a time-dependent magnetic field and you have a spin in this time-dependent magnetic field, it doesn't really matter whether it's spin 1/2 or spin 1 or spin 100. You can describe the dynamics of the system in terms of a certain object that doesn't care about the presentation, about the Hilbert space. And this appears to be very important, in particular because it explains, or at least illustrates classical to quantum correspondence which is basically the question of how to relate the dynamics of a closed quantum system to the corresponding dynamics of a closed classical system. And then I will, if time allows, I will discuss how this approach can be used for certain lattice models, quantum lattice models. Okay. Let me start with this introduction to Lie algebras. And actually, so this question goes a long way back, to the beginning of the 19th century, actually. So when Mr. Galois found that how to solve basically an arbitrary polynomial equation like that, so the solution for n less or equal to 4 was based on what is now known as Galois rule, which basically relates roots of the polynomial to the symmetry of permutations between its roots. And it turned out to be a very constructive theory, which allows basically people to prove certain interesting theorems and such. So an interesting fact about this gentleman is that actually he lived only for 21 years. So he was individual, I guess, or a woman or something. So, but he has contributed very significantly to mathematics, and this is perhaps the main contribution. So the main idea of Lie, this guy, was to use essentially an extension, generalization of Galois theory to differential equations. So, and he was wondering if there is a constructive procedure which may help you figure out the solutions to differential equations based on the symmetries that they have. And so this basically gave rise to the theory of Lie groups and Lie algebras, and this happened a long time ago. And so the motivation for us, which has existed of course a long time, to look into this particular theory of Lie groups and Lie algebras is that both classical equations of motion, let's say Newton's equations or Bloch equations for the spin, and the Schrödinger equation are certainly differential equations, and so where methods of Lie theory can be very useful. Okay, so this is of course very general introduction. So now, what is Lie algebra anyway? So basically, mathematically, it's nothing but essentially a vector space which has just one operation that we include, that is, well, let's call it commutator. Okay. And so vector space has a basis. So let's say these will be 1, 2, 3, 4, n elements, vectors, let's say. So to define a Lie algebra basically means to define commutation relations between the different elements. So the one famous example, let's say, is just SU2 algebra, which is related to spin, in which case these f's, which are known as structure constants, are simply this antisymmetric tensor. Now, so what is important about Lie algebras is that at this elementary level, so the products of different J's are not defined. So for my purposes, these J's will be associated with the operators in, let's say, in the Hamiltonian or something like that. But I don't really need to be able to multiply J1 and J2 or to calculate J1 cube. So these are additional operators which exist apart from the minimal Lie algebraic structure. And so it turns out that for a large class of non-equilibrium problems, you don't really need to be able to perform this operation. So this commutation is enough. So, and from this point of view, I will be talking about Hilbert space invariant representation invariant results. So basically, results do not depend on my ability to multiply things. Okay. So to make it maybe a little bit more transparent is that, again, so let's go to this is SU2 algebra, so which is, let's say, describes spin 1/2 or spin 1. They're both representations of SU2. So of course we can identify with spin 1/2, let's say, Pauli matrices, and for them it's very easy to define products. And also for spin 1, we can identify with them 3x3 matrices. So, as I will show, so much actually does not depend on these matrices. So the only thing which matters is the commutator. Okay, so if you are the things, and I will be done with the mathematical introduction. So this is a very huge, it's an enormous subject, mathematical subject, Lie algebras. I'm not an expert in it. I'm not going to try to pretend that I am. But there are a lot of things which are known. Okay, and there are some very useful results that exist. So so the results which are important for physics, at least for the kinds of problems that I'm thinking about, are the following main results. So two important formulas. So one formula is called Hadamard formula. Let's say we're thinking about, so this is an operator in my quantum mechanical problem, and I'm performing, let's say, a transform from a Schrödinger representation to Heisenberg representation to interaction representation. So I oftentimes have to calculate such products, and it turns out that these products do not really depend on the representation that I choose on the Hilbert space. They're entirely determined by the commutator. So this symbol that you oftentimes will see in the mathematical literature basically just means equivalent to the commutator. And it's very convenient because one can easily define the square of this operator, which basically means just double commutator, a function of this operator. So, for example, so this Hadamard formula can be written in this form. Another useful formula, and actually famous formula, is Baker-Campbell-Hausdorff formula, which allows you to calculate the products of two exponentials and relate it to another element in the algebra. And so it turns out that there exists actually a closed formula which has been derived. It's not very useful, but it exists, and it also manifests the fact that actually it doesn't really depend on the representation. It also only involves this commutator. So this symbol means a commutator, and this is just some function. Okay. Okay. So now, so the famous fact about Lie algebras and Lie groups is that essentially you may think about a group, a symmetry group. Let's say it's a certain space, a certain manifold, a certain space that you can visualize somehow. And so Lie algebra is basically a tangent space in the vicinity of unity operations. So it can be, so for any Lie group, we can identify a Lie algebra associated with it. So, however, generally we cannot restore the Lie group from an algebra. So, so there are different groups which have the same, the identical Lie algebras. And so this also turns out to be important. In mathematics, so Lie algebras are often considered byproducts of the Lie groups. But in quantum mechanics, it turns out oftentimes it is convenient to take the opposite view, to start with the Lie algebra and to try to restore the Lie group that it corresponds to. Okay, so now let me go maybe to a more physical problem. So let me start from the very basic thing. So let me consider a non-equilibrium Schrödinger equation described by some Hamiltonian which is time dependent. So if we have a finite dimensional Hilbert space, one can easily prove that any Hamiltonian can be written in this form. So it's a sum from 1 to d, d is some number, the dimensionality, and these j's are generators of a Lie algebra. It can be, for example, a spin in a magnetic field, in which case it will be just Sx, Sy, and then Z. Or it can be a driven harmonic oscillator, in which case it will be A dagger A, and A dagger and A and 1. So essentially any Hamiltonian can be viewed as a trajectory in a Lie algebra. So, and what we want from the Schrödinger equation, we want to find the solution to this, basically we want to find the wave function satisfying a certain initial condition. So instead of doing this, we of course can concentrate on the evolution operator, which relates the initial condition and the final state at time t. If we just plug in this relation into the Schrödinger equation, we basically get the identical equation for the evolution operator. So this u is now an evolution operator. And so of course this equation does not depend on any initial condition, it's completely decoupled from it. But what is absolutely important is that actually, even if we formulate our original problem in a specific Hilbert space, this equation actually does not depend on Hilbert space, and I want to show how this happens. So let me multiply this equation, the Schrödinger equation, by u dagger from the right. So since we're talking about a unitary evolution, u and u dagger is equal to 1. So therefore, the corresponding equation. Oops.
On this, on the Hamiltonian, basically you're writing down some, I guess, j's or some generators.
Yeah, some generators of an arbitrary problem. Basically, what I'm trying to say is that whenever you have a time-dependent problem formulated in finite-dimensional Hilbert space, you always can do that. It's not specific to any particular problem. It's always like that.
So suppose I have a term which looks like J squared.
Well, then I would have to enlarge my Hilbert, my Lie algebra and just include this J squared as another generator, commute it with everything else, and it may lead to a much larger algebra. But what I'm considering at this moment is essentially a non-interacting single particle problem that can be written in this form. So basically, it's a statement about matrices. So whenever you have a certain time-dependent Hamiltonian, you can always write it as a set of time-dependent matrices with some time-dependent coefficients that commute into one that flows under permutation. And that's by definition what is known as the Lie algebra.
If they don't close,
They do.
if they don't, no, but if they don't, you can always add the ones to close it, and then
Yeah,
the coefficients are zero.
Yeah, of course, yeah. So there, I should have mentioned that many coefficients may be zero. Yeah, of course, indeed. Yeah, that's true. That's true.
Can I ask?
Yes.
If J's are creation annihilation per some Fermat, is it also a Lie algebra?
It is a Lie algebra, but it doesn't have a finite dimensional unitary representation. However, it is Lie algebra. It is indeed also falls into this category. Basically, essentially, what I want to say is that from a physicist point of view, whatever problem that we're thinking about normally, which involves an essentially single particle structure, can be written in this way. And what I'm trying to say is that, well, I haven't said anything yet, so I'm about to basically make the main point, is that, so instead of looking at this equation, we can look at this equation, which is an equation for the unitary operator. So from the mathematical point of view, Hamiltonian is a trajectory in a certain Lie algebra. And so this U is essentially a trajectory in the group. And what I need basically from the theory of Lie algebras and from this mathematical theory that I was referring to is that I want to try this ansatz for the U of t. Okay. So it is known that in certain cases one can exponentiate the algebra back into the group. So any group element can be represented as an exponential of the Lie algebra. And so basically what I'm trying to say is that let's take this equation and let's make this ansatz. And instead of solving the equation for the wave function, let's try to solve for the equation for these guys, phi, which appear in the exponential. So this is sort of the main punchline. So if you forget everything else that I was saying, essentially, so this is enough. And in fact, this was suggested a long time ago by mathematicians, in particular by Magnus. However, he was concerned about more general equations, basically arbitrary differential equations that have this form. And it has been long known that in general you cannot find the solution that represented by a single exponential, but you can only represent as a product of exponentials. However, one can easily show that in quantum mechanics, at least whenever you have a finite dimensional Hilbert space, so you can in fact represent the evolution operator as a single exponential. And so the main point here is that if you do so, and if you manage to find this, what I call dual generators, so phi in this exponential, you solve the problem in any Hilbert space. For example, if you have a spin that is driven by some magnetic field, so these generators will be basically Pauli matrices, sigma x, sigma y, sigma z. Or you can have, I don't know, 100, spin 100, in which case it will be 100 by 100, or whatever it is, these matrices. If the magnetic field is the same, so the generators won't really depend on the representation. So this is completely invariant object. And if you happen to know it for particular representation, not for all representations altogether, yes?
You see, in principle, this, I believe it can be done. But now the question is it's really going to help, because you'll need to know how to exponentiate an arbitrary element of the algebra in order to apply it to a function. And that, for simple groups like rotational group, it's known, the bigger D functions. You see, so that's not a problem. But if you take an arbitrary Lie group, you see SUN, I think that's more difficult.
It is more difficult.
I don't know if you can really gain much by doing this.
So yeah, there is a paper which showed that indeed you can do something useful there, and but indeed, so if you have a very complicated algebra which has a huge
SUN, where n is 1,000, for example.
Well, then probably probably it's complicated, right? So, however,
Yeah,
what I'm
but
trying
that
to
would be an
say.
interesting case to study because it's for 1,000 dimensional Hilbert space. It's not so big.
I understand. Yeah. So, okay, there are possibly some problems where it is not a very practically useful thing, but there are also problems that I'm about to describe where actually it is very useful.
Okay.
So, and also I think it sheds light on quantum to classical correspondence. That basically one of the main results. So, if you want, so this is the main picture, the main slide of the first part of the talk. Okay, so instead of looking at the Schrödinger equation for a wave function, I can look instead for at this equation, which is the Schrödinger equation. Okay, so but instead of just solving it for an abstract u, I represent it specifically as an exponential of my generators, and this is some sort of time-dependent trajectory. And so the statement is that this particular expression does not depend on the Hilbert space, on the representation that you choose. Okay, so as long as you have agreed on a certain algebraic structure, so all representation, all Hilbert spaces will be described by this equation. Another interesting thing is that this equation actually you can derive it in certain cases. It doesn't contain the Planck constant, so in an explicit form for sensible physical theories, it wouldn't involve only real quantities. Okay, so and this is sort of the geometric picture responding to this equation. So in this case, I don't want to think about the Hilbert space. Instead, I'm thinking about the Hamiltonian. This is my Hamiltonian. So J's are the generators, whatever they are, of my algebra. So B of t is sort of a driving field, time-dependent field. And so this thing basically corresponds to a trajectory in the algebra. And so my task or the problem actually is to find the trajectory in the corresponding group. And this means to solve the problem. And if I have done so, basically I can find a solution for all Hilbert spaces corresponding to this problem. And so to connect it immediately to quantum to classical correspondence, we oftentimes associate a classical limit with a large dimensional representation of something. Let's say, spin 1000 is almost classical, we would say, right? So if I have managed to, formulate things in the Hilbert space in variant ways, so it means that probably, it will have some relation to classical limit. So another thing is, of course, the reasonable question: can we, instead of just looking at this thing, can we just derive, say, explicitly the equations for phi? And the answer is, in some cases, you can. Okay. So, in fact, so this structure was considered before by many people, including Feynman, and so there is. It appears again in mathematical literature, but it's normally not is not assigned any major importance. Yes, indeed. So the problem sort of relates to exponentiating matrices, but you can cast the previous equation into the following form. So phi, remember, phi is this a generator that I want to find. B of t is the magnetic field, sort of generalized magnetic field or time-dependent field that I have in my system. And so this is an equation that I have to deal with. So phi itself is a d-dimensional vector. Let's say for spin it will be phi x, phi y, and phi z. And so L here is a so-called adjoint representation of the algebra. Let's say in the case of spin it will be just simply rotations. Okay, so this is 3 generators. But it turns out that this equation is actually not specific to SU2 or whatever. So it is just general form that you can use. And an important thing about this equation is that one can prove that, first of all, as I said, so there is no Planck constant. If you start with the sensible physical theory, Planck constant will drop out from this equation. So it is unchanged in the classical limit. So another thing is that everything here is real. So these matrices can be shown to be real valued, and these functions can be shown to be real valued. So as long as you start with the Hermitian Hamiltonian. Okay, so now let me give you an example. So an example will be in this case.
If I take spin, for example, then okay, yeah.
So let me just take the spin. So this is not just the spin, it's spin 1/2. In my language, it will be a two-dimensional representation of SU2, it will be spin 1. And so one of the canonical problems that appears in many fields of physics, so here I showed a few applications, is a driven two-level system. Okay, or basically a problem that belongs to my class of problems that I'm interested in. You have some time-dependent field, and you have here, well, just Pauli matrices in this case. So this realization, for instance, is a qubit. Well, qubit is a two-level system. You may drive it, so it's described by that. Another problem is actually defects, let's say, within the qubit, which themselves oftentimes are two-level systems. And so this question oftentimes pops up. So an interesting fact about this equation is that it looks deceptively simple, but it's not solvable in closed analytic form for an arbitrary dependence B of t. So it's hard to believe when you first look at it, but it's true. So there is no closed solution for basically for the wave function corresponding to an arbitrary B of t. Okay, so and why is it so difficult to solve? Actually, it again goes back to well, a long way. So if one can in fact rewrite okay, this two-level system problem. So in this case, I have picked a particular form of this time dependence. So one can rewrite this 2x2 matrix, let's say, and introduce a new variable. In this case, it will be just the ratio upside down and upside up, and reduce it to the so-called Riccati equation, which is a nonlinear differential equation that has been studied for 400 years, and it has no analytical solution only in a few limited cases. So it's very unlikely that we will just be able to solve an equation that is unsolvable. So, let's try to take a different perspective. So instead of solving for the wave function, let's try to solve for the unitary evolution. In this case, it will be spin 1/2, but it could have been spin 1, doesn't really matter. So, and we basically use this ansatz, and we use this what I called two-dual Schrödinger equation. And so here we specifically have to use the rotation matrices. And it turns out that you can calculate this thing, and you can find a specific realization of this equation for SU2. So one amazing thing, I haven't seen this equation elsewhere, but it's probably important. So basically, this is a specific realization of this equation for SU2. For SU2, you have sigma x, sigma y, and sigma z. Therefore, phi is a three-component vector. So let me parameterize this vector with a modulus and a direction. So this modulus is a positive number, and n is a unit vector on a two-dimensional sphere. So this is my parameterization. So if I do so this is the equation that I get instead of the original Schrödinger equation. I haven't really done anything. So I have basically what I have done, I have written the Schrödinger equation, introduced the evolution operator, multiplied the Schrödinger equation by U dagger, and then I use this ansatz. And this is the result of this exercise. So, what one can observe is that, well, I got some interesting nonlinear differential equation, and well, it may be hard to solve it. But for example, if I know what evolution I want, if for instance I have the problem of okay, I have a qubit and I want to rotate it into something, I want to introduce some unitary rotation. So the inverse problem is almost trivial. If I know the solution for this unitary evolution operator, I just plug it in here, and I will get the exact driving field that will give me the corresponding evolution. And so this is actually typical for these sorts of problems, sort of linear in these algebraic generators.
So,
Yes.
if you know how you want to move it,
Yes.
this guy, this equation star gets you the evolution of B. You have to use the Schrödinger equation
Yes.
to get how the
Exactly.
n vector should move.
Exactly. Yeah. So basically, so if you, for instance, you pick any phi you want. Let's say, I don't know, you go from North Pole to South Pole by some trajectory on the sphere, and it's up to you to choose it. It may be a very complicated trajectory. Then you just pick, phi, plug it in here, you get the exact driving field that will actually enforce this evolution. This is first statement, which is true for spin 1/2 and actually for any spin. But that's another important thing.
Can I ask
Yes.
a question? So suppose somebody gives me a wave function psi of t for a spin,
Yes.
and ask me what kind of Hamiltonian would give me this psi of t. I would think, well, the Hamiltonian is a unitary, transformation matrix which takes psi into the psi t according to the Schrödinger equation. So I should be able to figure it out. Now maybe it'll take me a few more steps than just using this formula. So isn't it some kind of a simple problem?
No, I don't think so. Well, at least, I've seen a lot of papers which discuss how to, well, we want this evolution, how to find the field, okay? So there is a literature on that. Maybe I'm wrong.
So it is such that h of psi is equal to I div psi dt. Given
Right.
psi, I should be able to find h, although maybe.
Okay,
You know,
so
take it in steps.
let me go a little further. Because this is definitely not the only thing that I wanted to talk about. One implementation of this thing actually is related to topological insulators that were discussed here. And I'm not going to give a lot of introduction. The only thing I will say is that the topological insulators that are currently discussed are basically non-interacting models. Okay, so the question, essentially you have some Hamiltonian, which is basically a tight binding model, and you have an internal index, which may be spin or pseudo-spin, whatever it is, and this tight binding model involves essentially this sort of effective spin-orbit interaction. And so if you have a lattice and you have translational symmetries, you can perform Fourier transform, you will rewrite it in this form, and you get this matrix, which is Fourier transform of these hopping elements. And the question of topological classification of lattice models, essentially question of topological classification of matrices like that. Okay, how it appears is well, of course, if I have translational symmetry, I can use just the block theorem. So the wave function can be written as a periodic part of the wave function times this u, and this p is momentum. If I have periodic boundary conditions, so Brillouin zone is a torus. So in each point on this torus, I have this u of p. So therefore, essentially, topological classification is basically based, at least in 2 dimensions, on the topological classification of these fields on the torus. Okay, so that's why you get the Chern number-like things, and you can associate the topological indices with certain observables, such as the appearance of the H states, for example. Okay, so the bottom line is that topological insulators is a classification of matrices if you're not talking about interactions. Now, if so can we classify non-equilibrium matrices on the same footing? So basically, and this is what we did with Lindner, Raphael, and somehow it's going to be published in Nature Physics. So basically, is the question of what happens if you have a time-dependent Hamiltonian, time-dependent lattice model, and in particular, if you have a time-dependent lattice model where the time dependence is a periodic function. Okay, so yeah, it turns out that indeed you can just basically use the existing classification for equilibrium topological insulators to this and go to this non-equilibrium problem. And what is important is that if you have a periodic Hamiltonian, if h of t is equal to h of t plus some period, so the corresponding evolution operator that I was just talking about has this form, and it's called basically the Fouquet theorem. It's essentially the analog of the block theorem, but in time now. So u of p of t is basically the solution of this equation, which is very similar to the Schrödinger equation I described before. And the statement is that if you have a periodic time dependence, so the solution operator has a periodic part and this exponential part, which is called Fouquet Hamiltonian. So this guy here is called Fouquet Hamiltonian. Is time independent. And it turns out that basically the topological classification of these non-equilibrium problems with periodic drive reduces to the topological classifications of this Fouquet Hamiltonians. And using how is it relevant to what I was just describing? So if, for instance, you can start with a model that is topologically trivial, and then add to it a term which depends on time. And you may ask whether by enforcing a certain time dependence you can drive the system into a topological state. And the answer is yes. Okay. And in particular, how to construct this state is essentially use this reverse engineering procedure. You start with an answer that you want to get, which is the topological state, which is, for instance, a matrix that satisfies certain properties that you want from it. And then you use this sort of reverse engineering to see what kind of time dependence you need to impose onto your system so that it gets this type of evolution. And so this is not exactly what we did in the papers in these formal terms, but so the bottom line of the paper that I referred to was that you can start with a trivial model, add a certain time dependence to it. Physically, it can be, for instance, shining light, on the two-dimensional quantum well, which is in the trivial state, and drive it into topologically non-trivial state, such that the edge states appear, all the hallmark phenomena appear. Yes.
So just the main question is that it's going to be exactly the same classification, but now mainly I think of classifying topological spaces as non-interacting terms, say counting some topological numbers of filled bands, and then there's unfilled bands at higher energy.
Yes.
But now if you have a kind of a periodic energy space,
Yes.
what are the lower bands and what are the higher bands?
So it's a very good question. So I would say that topological classification of equilibrium Hamiltonians is basically, first you have to classify the bands. You don't say anything about how they occupy. You attach chart number, let's say whatever you want to attach to each
That
band.
you can do here.
Yes. So and then you start populating those bands, and they may or may not be an insulator. Now here, what happens is that it turns out that this operator, this new Hamiltonian, becomes, basically the Hamiltonian we have to deal with, and this Hamiltonian classifies this Hamiltonian gives rise to the new bands. They are good labels now for your states. Now the next question, how they are populated, which is a good question.
Sure, yeah, that's one question. But another question is maybe you can get even a more elaborate topological structure because now you have a kind of compact space also in energy direction.
Yeah. So this is not what we did, but you did this very session I did.
I believe you see that this partition of the representation of the unitary operator, in the particular case you study, for example, Berry space, the first fact is the topological Berry phase, and the other one is what he called dynamical phase. You see, so I think it's directly related.
Yeah, it is related.
And it's also related to the non-adiabatic Berry phase. You see the first factor.
So basically, this theorem, which is just a statement about how the solution looks like, doesn't require adiabaticity. It may mean
you don't need it. You see, that's the problem. You don't need for that representation adiabatic.
I don't think it's a problem, and I would say it's good. Okay, so it applies in particular for diabatic motion, but not only for diabatic motion.
So that's valid in general.
Yes, indeed, yes. So, yeah.
So when talking about Berry phase, one thing I'm wondering about is the Berry phase does depend on representation. Like if you have this geometric phase, it's proportional to the spin, whereas what you wanted to tell us, as I understood it, was that this is a story that is independent of the particular value of the spin. It just depends on the algebra.
The statement that I actually made is the following. So you can, well, not for this particular problem, but in general, you have time-dependent Hamiltonian. You can represent a unitary evolution operator in such a form that, in this form, where phi does not depend on the representation. So if you have spin 1/2 in this field, and if you have spin 1 in this field, all you have to do to find the unitary evolution is just replace Pauli matrices with spin 1 matrices. So this will give you the exact solution. So it's exact. If you have, I don't know, spin 100, you will do the same thing. You just have to, put their corresponding matrices. But I'm not making so. How it's relevant to these topological insulators is the following. So if you know the solution that you want to get in the time-dependent problem, so this equation is an effective means to find the actual driving field that will give it to you. Okay. So you may start with spin 1/2 problem. For example, you will find, let's say, what you want from it, so which is topological insulators, presumably in this case, driven by some time-dependent drive. And by doing this reverse engineering, you will find exactly the Hamiltonian that, it may be complicated Hamiltonian, but you will find some specific Hamiltonian that will give it to you. So that's the statement that I made. But whether or not the Berry space is representation dependent, that I don't know, that I haven't discussed. Yeah.
Well, I was really, Ava had mentioned that. So I mean, it's well and good to classify the bands of the evolution operator,
Yeah.
and the quasi-energy bands,
Right.
by Chern numbers. But it's not quite clear to me what the actual density matrix of the system is. I mean, there's actually a vast sort of Russian literature on this. I think
I know.
dating back to your grandfather.
I know. Yeah.
And I don't think it's completely understood. What I mean, if you and it may depend on the mechanisms of how you're having relaxation and coupling to environment and whatnot.
Yes.
But if you just say, well, I'm going to assume that I have an entire Floquet band that's occupied. Yeah, you could identify a Chern number with that. But if you would you actually measure that? Also, if you took a Floquet band and you represented that in terms of your original time-independent basis states, you could have significant population of the higher band. If you worked out the energy density in that, you'd find that when you turned off the the signal, you'd have like a nuclear bomb or something. I mean, so I guess I'd like to understand better what the actual density matrix is.
Right. So I think there are two questions. One question is this Floquet bands, which just provides you labels with classifying your states. And the next question is how they are populated, which is related to relaxation process. You have to actually write some kinetic equation, solve it, which is impossible by analytical means. However, if you have relaxation of, if you have separation of time scales, for example, so if you have, let's say, some energy relaxation time, and you have, well, the corresponding time, characteristic time of your time evolution, they're usually, well separated. At least it's in your hands to make them well separated. So you can at least cook up a scenario in which you're sure, at least at some time scales, you will see some manifestations of this Floquet topological installation. So this is the only thing I can say is that it's possible to have these H states, non-equilibrium H states. In the end, of course, you may have thermalization, you may have all kinds of things, and it is very non-universal problem, and it's not solved problem.
What time scales you would need?
For what?
To realize this topological thinking.
So, for instance, if energy relaxation is relatively weak, so if, for instance, collisions are not very...
this is actually the bad process, but the good process for you is the time scale for you.
Well, I mean, they are related. So if there are no bad processes, as you put them, so there is essentially no thermalization in the system, you will prepare some state will stay in some non-thermalized version forever. It's not never going to end up in a final temperature state. But it's something which never happens. So you have to include relaxation, and so the time scales for your periodic drive have to be related to this energy relaxation. What I'm trying to say is that it's better perhaps to have energy relaxation times large. So in other words, interactions relatively weak. To be able to have some intermediate time scale where you can actually see that.
If you envision that when you drive it, then it has to relax in some way. But
so there are several things you can do. So for instance, you can have a quasi-stationary state where you have a bat, let's say phonons or something. You pump some energy into your system, but it immediately gives it to the phonons, and it just it exists in some quasi-equilibrium state. So the distribution function doesn't necessarily have Dirac or potential depending on what you have. So this is one scenario. Another scenario is that you just start driving your system. It doesn't have time to relax into anything, but it just goes into some non-equilibrium state which has these topological properties, meaning that it has H states circulating around the boundary and everything like that. So, but when the interactions kick in, so you will lose this state, presumably.
yeah, this was my question concerning the latter one. Suppose basically you're given the state where you drive it. What are the time scales you're talking about?
Compared to what?
Just a number.
I don't know.
Is it a minute?
I don't know the number. So yeah, so it's so actually well for this particular system, it's probably terahertz. You have a certain gap.
For any well, I don't know about the microwave. For any driven system, basically, that's a little bit higher energy than microwave. The let's say electric maximum electron relaxation time for 30 seconds.
I don't know. I mean, perhaps. I'm not convinced about that. And also, I think it's very non-universal, so I'm not sure about that. So I would say the relevant relaxation, the relevant time scale should be related, first of all, to the parameter theory of Hamiltonian, in which case it is basically the gap, the inverse gap, something like H or delta.
Well, there is always Coulomb.
Okay, yeah, so I haven't considered the Coulomb. So I think so one line is that, first of all, there have been experiments, actually, not on topological insulators, but on systems such as superconductors, where people have induced superconductivity by external irradiation. So it's not inducing a topological state, but it's inducing a very fragile state. So it's possible there. I don't see why it's not really possible here. So there is a theory of Eliashberg, for example, which he explains. I don't know if you're familiar with that. So one line is that it's non-universal, but I think this.
Can I ask another?
Sure.
Sorry,
Yeah.
another question. So, do you have examples where h of p and t at every fixed t is not topological, but f of t is topological? You can look at h of p and t for a fixed t as a Hamiltonian, just type in Hamiltonian. So, is it possible for it to be always non-topological and f to be topological, meaning topological and non-trivial, or do you need to have some h in the course of the evolution to become somehow?
Yeah. So basically, there was a specific model that we considered, which is this.
The answer is yes.
Yeah. So the canonic model of
Yes, it's
Yes.
possible to.
Yeah. So and
Now, you're radiating this this quantum well, which is not topological, but you're driving it to be topological.
yes, yes. So, but you have to add a term to a Hamiltonian. It's not that it magically appears. You add a term to your Hamiltonian, which on average is sort of zero. So, but
at every fixed time, the term does not make it topological. At any fixed time, within the Hamiltonian and studied as a time-independent Hamiltonian, for any time, this will be a non-topological Hamiltonian. And yes, right? That's how I understand the answer. Yes.
You mean that, no. This probably. I don't know the answer. So I don't know the answer. So what we have looked at is that you start with a non-topological Hamiltonian. You add to it a time-dependent term, which on average is zero. However, it drives it into topological state, and if you solve exactly the corresponding problem, it does have H state, it does have all the hallmark properties of the topological insulator. That's the only statement I can make.
Can I just make a remark since I guess we have time for the same time. But, well, actually, so, 20 years ago with Patricio Booth and Jorge Kirchen and Mario Feingold, looked at a model of the following. Ostensibly, so absolutely do with quantum chaos, where you have these kick systems. You have a Hamiltonian, which is like a kinetic energy, which is a function of momentum, plus a potential, which is a function of coordinate, times a kicking function, like a Dirac cone. Okay, it would be equivalent to having, let's say, a kinetic energy operating for one part of the cycle and a potential for another part of the cycle. Now compute the evolution operator for that. And so it's like what Victor is talking about here. It's actually like in the classical model, just why you can increase your amplitude when you go swinging on a swing, and this sort of parametric resonance. So in that case you can think of in that case you put the model on a torus, and then it's sort of like a has some you get some sort of quantum Hall type physics there. But at any given instant of time, your Hamiltonian is either cosine of p or cosine of q. Okay, but then you multiply them together, e to the I lambda 1 cosine p, e to the I lambda 2 cosine q, to form the evolution operator. And then as the lambdas get bigger, you have level crossings, and the states you get this diffusion of Chern numbers, and more of the quasi energy bands acquire this topological character. So you can, but at any given instant of time, you have a sort of totally trivial Hamiltonian.
Yeah. So this particular topological insulator thing was just a remark on how one can presumably use this equation that I like for whatever reason to get something interesting. But the main result that I wanted to convey was actually this. So, and I think I'll have 5 minutes or 10 minutes or what I think the official title of my talk was involved the notion of quantum to classical correspondence. Okay, And basically, let me just briefly review what I meant by that. So I started with this particular equation, which is just the Schrödinger equation, nothing more than that, with some arbitrary driving fields and some generators that satisfy certain commutation relations. So this could be harmonic oscillator, spin, whatever. And so these are the structure constants, which is the main object that I need. So if I'm looking at this particular standard Schrödinger formulation, what I'm interested in is the evolution of the averages. For instance, if it's a spin, it would be, let's say, magnetization as a function of time. Or I may be interested in certain correlation functions, well, it should be T2 here, between different operators, let's say spin-spin correlation functions. Well, so if you use just the usual Heisenberg equation of motion and take advantage of knowing these structure constants, you can easily derive the corresponding equations, which are sort of, we'll call them generalized block equations, which is basically the equation for evolution of this average. So for example, if you have a spin, so this will be simply the block equations on a sphere. If my algebra happens to be A dagger A dagger N1, so this would be nothing but Newton's equation, well, Hamilton's equations of motion. So these equations are as classical as they get. So if there is anything classical about this system, or if you want to consider its classical limit, so this is probably the equation that you would want to write. And so the question that one can formulate is how to relate the solution of this equation, of the Schrödinger equation, to the solution of this equation. So this is basically the question. And it turns out that it's basically the same thing. So this is what I want to illustrate on this, again, on the example of a single spin. Let's say spin 1/2. So quantum spin dynamics will be the following. So it will be your evolution operator, which is determined by this particular trajectory, phi of t, exponentiated and acting on the initial condition. And these are 2x2 matrices. So you can prove quite easily that the solution to the block equations with the same driving field that you had in the quantum problem can be written in this form. So magnetization is equal to the exponential of the same phi of t, it's the same object, times L, where L is just the 3x3 matrix generators of rotations. So it's just two-dimensional representation, three-dimensional representation. It acts on the initial condition. So let's say this is your initial magnetization, this is your final magnetization. So quantum to classical correspondence is basically the fact that you have the same functions here and here. And so it is not specific to the spin, I think. So it's if you take essentially any problem, you formulate it in sort of Hilbert space. You happen to be able to find your evolution operator. You can always write the solution of the corresponding classical equations. Let's say in the case of harmonic oscillator, it will be basically translations, Galilean translations. And in general, classical dynamics appears as a certain action symmetry group and some classical manifold. In this case, it's just block sphere. In the case of harmonic oscillator, just a plane, x and p, etc., etc. But this is, I think, this is sort of the main message. So you have a quantity which sort of connects the two things. Okay, so now about the Berry space. Actually, there was a question about the Berry space. So if you think about Berry space, it seems that Berry space must be lost in the classical description, but in fact it's not lost. But how to see this is the following. So the equation for the evolution operator is an equation for unitary matrix. Okay, so it belongs to the SU2 group. So SU2 group topologically is a three-dimensional sphere, which I cannot draw, but I have found some illustration in
it makes it much clearer.
Yeah. Right. So on the other hand, classical equations of motion are equations, basically equations of motion of the block sphere. This equation of motion of a classical magnetic moment. And there is a known relation that three-dimensional sphere modulo S1 is equal to S2. So, and this is, by the way, called Hopf vibration. And so this U1 is exactly the Berry space that sort of that we would associate with this problem. And it does disappear in the equation for the averages. However, For instance, for example, if we study correlation functions, let's say for the spin, so they will depend on the gray spaces. It's not really, it doesn't, it's not really lost completely. Okay. So, and let me just take, maybe 3 more minutes and show you just one slide illustrating. Okay, let me just skip this stuff. Illustrating how this, in principle, could be useful in more interesting interacting lattice models. So what I discussed is actually sort of trivial single particle model, and so basically it's a model that is linear in the generators of a certain algebra. So what we're interested normally in many body physics is are interacting models, let's say on a lattice, when you have, let's say, interacting spins or interacting bosons. And basically, all the variety of all such models can be written in some sort of generalized form, so where J's will be the generators of some algebra. But instead of just having a single linear term, you are allowed to have interactions between these terms. And it turns out that the question of thermodynamics of such systems can be formulated. Well, unfortunately, it's a little bit technical. Basically can reduce to the same sort of dynamical system that was discussed before. So, for example, if you have an arbitrary problem, it can be a spin problem or any other problem, you have interaction between 2 elements, let's say on different sides, you can use this algebraic identity to introduce basically a Haber-Stratonovich field in the path integral. And but instead of trying to calculate the path integral, you can prove the following identity for the partition function of the model. So you start with your lattice model, you write the corresponding path integral, you decouple the interaction term by the Haber-Stratonovich field, and what you can prove is that the partition function of this type of a model will be essentially a linear combination of the traces of some evolution operators, which are driven by Hamiltonians associated with these Haber-Stratonovich fields. Okay, so the only thing I want to do is to show you one example and to show you how it can be useful actually, and how for actual calculation. So let's consider just a toy model, and this toy model will be simply a maximally frustrated spin model. So let's say you have a bunch of spin 1/2, and they all interact with each other via some antiferromagnetic interactions. It's not really the most burning problem in condensed matter physics, but I just want to illustrate a certain concept. So for example, if you want to calculate the partition function of this particular model, you can write the path integral and decouple terms, the interaction terms in your action or in your Hamiltonian. So instead of having these interactions, you can have linear terms in your Hamiltonian, but those will be associated with some dynamic Haber-Stratonovich fields. But instead of trying to calculate this basically unsolved path integral, you can notice that if you roll back this path integral formulation in the Hamiltonian formalism, you can rewrite it in this form. So you can write it as an integral over all possible Haber-Stratonovich fields with some Gaussian decay, and here it will be the trace. In this case, there are n identical spins, so to the power n of some evolution operator calculated at b beta, which is 1 over temperature, associated with this equation. Delta of t is my Haber-Stratonovich field. Rho of t is essentially evolution operator, and sigma are just Pauli matrices. Okay, so and it's a very complicated problem, and it actually has a sign problem there, because if you go back to the original formulation, it has plus and minus terms, negative and positive terms appearing in the partition function. But now one can use the following trick. So here we integrate over all possible sort of magnetic fields that act on the spin. Okay, so this is the partition function of this model, delta of t is Haber-Stratonovich field, and I have to integrate over all of them. Instead of doing this, I can start instead with the solution to the problem, so which I know has this form always. There is always some evolution operator described by some phi of t, and instead of integrating over delta, I can integrate over phi, since I'm interested in all possible evolutions. So the kind of motivation for this procedure is that I don't really have to solve this dynamical system. I don't have to know the solution because I can just basically immediately find the trace of this operator by elementary identities, which is the cosine of phi of beta. And so this term, which is unsolvable in the usual formulation, becomes trivial. However, and I also have a relation between this phi of tau and delta of tau. This is my magnetic field that drives the spin, and this is the solution to the corresponding equation. So this simple terms becomes relatively complicated. So it has this form. This complicated term becomes very simple. But another thing which is kind of interesting is that this expression for the partition function does not have a sign problem at all. So everything is real. Okay, at least if n is even. Yes.
Is there a Jacobian for this?
Yes, there is a Jacobian. Yeah, I didn't write it because it didn't fit. There is Jacobian which is simple. Yeah, it's simple and unremarkable. But huh?
It's positive ever.
Yes, Jacobian is absolute value. I'm sure we can. But sort of the bottom line is that if you think about certain interacting lattice models, you can rewrite them in terms of linear combinations of a single particle or single algebra, whatever you want to call them, dynamical systems. And in this formulation, in certain cases, it appears that there may be, you can derive expressions that don't have the sign problem, like this one. Okay, and I don't think it is specific to this particular model. There are some other models which also share this property. Okay, so of course, unfortunately, so this stuff is pretty technical. So let me just skip everything else and conclude. So it's, oops. And okay, I have tried probably not very successfully to convince you that so these Lie algebraic methods or way of thinking about certain problems are powerful and useful methods to study various quantum systems. I think it's an important thing that quantum dynamics of systems with finite degrees of freedom of closed quantum systems is actually decoupled from the Hilbert space and can be analyzed completely independently of it. Sometimes it is useful. And this sort of dual Schrödinger-Bloch equation is a useful means to solve these problems in certain cases and to establish classical to quantum correspondence in that, the evolution of a wave function occurs basically is driven by the same generators as appear in the evolution of classical averages. And what I didn't have time to talk about is that quantum lattice models can be considered as problems of interacting algebras where the corresponding methods are useful. Thank you.
Questions? That's the second speaker again. Break before we move to the last two talks. Maybe someone wants to talk about it. 5 minutes.